So this is the second video really in relation to gaseous exchange. And remember, we look at gaseous exchange at the lungs and at the muscles, the external respiration and internal respiration. And last video we looked at how this occurs at rest. This video specifically looks at during exercise, how gaseous exchange is changed. And we also have to link those changes to a graphical or a curve related expression of these changes. So it's quite a lot to get through. So again, the spec says we're looking for what changes happen in gas exchange compared to rest, where gas exchange happens at the alveoli and the muscles, and this is during exercise. Specifically, be able to explain accelerated dissociation of oxyhemoglobin. It's a bit of a mouthful, but basically all it means is explain why hemoglobin will give oxygen to the muscles more quickly. So hemoglobin is quite central to this explanation, and you should already know that hemoglobin is in the red blood cells and it is critical in terms of transporting oxygen around our body in the blood. So hemoglobin on its own is an oxygen transporter, and oxygen attaches to it to become oxyhemoglobin. Now, heme means blood. There's also another similar thing called myoglobin. Now, myoglobin looks after oxygen in the muscles, and you already might know that myo kind of refers to muscles. So heme is blood, myo is muscles, and these are things which hold oxygen. Importantly, perhaps be aware that hemoglobin can hold 4 pairs of oxygen. So 4 pairs of oxygen. And when hemoglobin has oxygen, we can describe it as being saturated. When it's full up with those 4 pairs of oxygen, it is fully saturated. And we would hope that blood leaving the alveoli at the lungs leaves fully saturated, having diffused oxygen into the hemoglobin, and it is topped up. Also, it then goes to the muscle cells, where it will let go of or drop off some of the oxygen before returning back up to the lungs to get topped up again. So we've got this ongoing process of oxygen being attached to hemoglobin and oxygen being dropped off hemoglobin. Except for we've got to use some language when we explain these things, and we'll look at those terms in a minute. At rest, only about 25% of the oxygen that hemoglobin holds diffuses into the muscles. So if I go back to this image here, remember we've got perhaps 4 pairs of oxygens on a hemoglobin. As the hemoglobin goes past the muscles, only 25% of its oxygen will diffuse into the muscles at rest. So that might relate to maybe 1 of the 4 pairs of oxygen. That would be a quarter, 25%. So at rest, 1 drops off, which means when it comes up here to the alveoli, it's got to pick up 1 to fill up again, and so on. So at rest, only about 25% is diffused into the muscles. In exercise, however, we might expect something different, and always go back to logic. What would we expect different? Only a little bit of oxygen dissociating or going into the muscles? No, we would expect much more. So here's the key terms that you must now know and use. Oxygenated blood is blood which has lots of oxyhemoglobin, hemoglobin carrying a lot of oxygen. Obviously, deoxygenated is blood with less oxyhemoglobin in it. So typically, arterial blood is oxygenated and venous blood is less oxygenated, is deoxygenated. Now, some big old words basically to mean attached to or drop off from is association. So at the lungs, the hemoglobin or the oxygen attaches to the hemoglobin, and that would be called association. So at the lungs, association occurs. At the muscles, the hemoglobin releases or drops off the oxygen so it can be used by the muscles, and that's called dissociation. So maybe you remember that with association is where oxygen attaches and dissociation is where it drops off, or loads or unloads, all phrases that are important to use. I've used this term quite a bit already, but the saturation describes how full up the hemoglobin is with oxygen. So if it's got its 4 pairs of oxygen as it leaves the lungs, it will be described as being fully saturated. And even in exercise, our hemoglobin tends to leave the lungs fully saturated. The sort of scenario it might not leave the lungs fully saturated is maybe at altitude, where we've got less oxygen in the atmospheric air to diffuse into our hemoglobin. A key thing also is how we describe hemoglobin's affinity for oxygen, how much it's attracted to it, or it is how it bonds together, how strong is the bond. So hemoglobin has quite a high affinity for oxygen, and that means it has quite a strong association or desire to bind with it. I've kind of answered this already. Where would you expect these two things to happen? You'd expect association to happen at the lungs. The hemoglobin attaches some oxygen, and dissociation occurs at the muscles. It drops off the oxygen. So the relationship between oxygen and hemoglobin is absolutely critical in being able to explain dissociation and association in exercise and the dissociation curve. Essentially, these are the key components. Now, where hemoglobin is in an environment where there's a high partial pressure of oxygen, you need to know that it will associate with oxygen. So this might happen at the lungs, where there is a high partial pressure of oxygen at the alveoli, and this is where hemoglobin holds on to or associates with oxygen. So remember, where there's a high partial pressure, hemoglobin holds on to oxygen. Conversely, where it passes through environments with lower partial pressure of oxygen, hemoglobin will dissociate oxygen, it will drop off oxygen, it will unload it, it will become less saturated. This might occur at the muscles. So where there's a low partial pressure of oxygen, hemoglobin lets go of its oxygen. And if you can remember those two phrases, you'll explain a lot. So it's all really about the loading and unloading, the associating and dissociating of hemoglobin with oxygen, and when this occurs. And this dissociation graph that we've got to really understand describes this. So let's look at logic. Logic is that at the alveoli, and we're going to go at rest to start with, so this graph will describe what happens at rest. At rest at the lungs, we know there's a high partial pressure of oxygen. Now, if we follow this line up, this describes how saturated hemoglobin is. This is the partial pressure, this is the percentage of saturation of hemoglobin. So where there's a high partial pressure, for example at the lungs, what we find is, going across, hemoglobin is practically fully saturated, nearly 100% full. The other thing we notice is where partial pressure drops, let's say to 40, we might find this at resting muscles. If we follow this line up, this curve suggests that hemoglobin only now is about 75% saturated. About 25% of its oxygen has been released, and we've described this already. So at the lungs and at resting muscles, we have a 25% drop in the hemoglobin saturation. So at rest and during exercise, the partial pressure at the lungs is high, always high, which means that hemoglobin associates and leaves the lungs almost fully saturated. So because there's a high partial pressure, the hemoglobin is holding on to oxygen. As the partial pressure drops to the example maybe of resting muscles, hemoglobin dissociates a little of its oxygen, and that might equate to one of its 4 pairs of oxygen. Only 25% is given off to the muscle cells. So the oxyhemoglobin dissociation curve explains gaseous exchange that takes place at the lungs and at the muscles, and what we know, that was describing the situation at rest. What we know in exercise is that we drop off, we dissociate more oxygen. Logically, we want to give more oxygen to our muscles. Now, I think the best way to approach this is kind of 2 mini steps. There are some physiological change. When you're exercising, there are a few things that happen physiologically. And we'll look at one physiological change that increases the gradient. So that will explain why more gas might dissociate. And 2, we'll look at 3 physiological factors that change hemoglobin's ability to, or willingness to, hold on to oxygen. Let's look at step 1 then, the gradient. Well, we know that resting muscles might have a partial pressure of oxygen at about 40 millimeters of mercury. We know logically that when muscles are exercising, the partial pressure of oxygen in those muscles will drop. So the first thing is pretty obvious. The gradient where there's a high partial pressure in the lungs or in the blood from the lungs and an even lower partial pressure in exercising muscles, we will have a greater concentration gradient, and therefore more oxygen will diffuse from the hemoglobin and go into the muscle cells. So during exercise, the VO2 of the muscles increases. So as in more oxygen is used by the muscle cells. Therefore, there's a lower partial pressure of oxygen. From here, 40 is resting and 20 is exercising muscles. This in turn increases the concentration gradient. So we've got high 100, 105 millimeters of mercury in the capillaries, and we've got maybe 20 now in the muscle cells. And that means that more oxygen will dissociate from hemoglobin and diffuse into the muscle cells. That's logic. Now, 20, following up to this curve, this resting curve, the original curve, shows that hemoglobin might now in exercise be about 35% saturated. It will have given off, it will have let go of, dissociated even more, 65% of its oxygen. It was only 25% at rest, and now it's giving even more oxygen off to the working muscles. This makes sense. The second step then, the 3 physiological factors affecting hemoglobin. These 3 things affect hemoglobin's affinity for oxygen. 1, we might produce some lactic acid, which increases the acidity in the muscles and in the blood, and this the consequence of this is called the Bohr shift. I'll show you that in a moment. 2, we have more carbon dioxide. The more our muscles work, the more they produce carbon dioxide. 3, temperature goes up. A waste product of making energy and using our muscles is we get warm. Our muscles get warm and the blood gets warm. So the combination of those 3 things changes hemoglobin's affinity for oxygen. And these 3 things make sense. The more you use your muscles, the less oxygen you've got in your muscles, and the more CO2, lactic acid and heat you might produce. So those 3 physiological things, the CO2, the lactic acid and the temperature, they basically reduce hemoglobin's affinity for oxygen. They make it keener, more willing to dissociate it, to let it go. And I mentioned the Bohr shift, in particular the acidity and the temperature. These affect this curve, these change this curve. And the movement of this curve, the alteration in this curve is called the Bohr shift. Now, the black line here is the original dissociation curve. Now, the Bohr shift actually moves this curve to the right. So what this means is where we've got a 20 millimeter of mercury or even less, a lower value for the partial pressure of oxygen in our muscles, if we go upward, instead of using the black line, which would have made it about 20, we might use the dotted grey line, which could be anywhere between 10 and 15% saturation. And this means that our hemoglobin will dissociate even more. Those 3 physiological changes denature the bond between hemoglobin and oxygen. They make hemoglobin unable to hold on to the oxygen, make it release it even more. And that is logical. That is what we want to do. We want to let more oxygen go from our hemoglobin. So in summary, the Bohr shift, that shift of the curve to the right, and the reduction in the partial pressure of oxygen in our muscle cells, which increases the diffusion gradient at the muscle cells, those combine to basically make hemoglobin less saturated, release more oxygen to the muscle cells, which is what we need to happen. At rest, it dissociated about 25%. During exercise, it might release or dissociate maybe even 75% or more. So at rest, maybe 1 pair of oxygen. In exercise, maybe 3 pairs of oxygen from the hemoglobin are released for the muscle cells. All very logical. So have a pause of this, have a look at this graph. It's just a simple version of it. And then the same principle kind of applies to carbon dioxide. The diffusion gradients between carbon dioxide and the muscles increases, so more carbon dioxide moves from the muscles into the blood, and therefore more carbon dioxide returns to the lungs and the blood and will dissociate out of the lungs.